All right, so about the exercise 6, let's take a quick look at the exercise itself. Whoa, what is that plus doing here? Plus exercise. Okay, so basically we are starting from the exercise 5, this stop and notch filter. So this is this exactly the same as on that IIR exercise. And then basically the second one is, well, here you get a 3 point basically. Here you need to work on that afterwards on that 3 points. So basically now you would quantize the filter coefficients to 8-bit accuracy. I show you a couple of ways of doing it. The hard way and the fast way. On the other hand, you cannot use the fast way unless you understand the hard way. There are no free meals in DSP, have you noticed? Okay, so basically on that one we had a situation that, let's see. Okay, on that exercise we had a situation that we had the unit circle, and there on some angle here you had the 0 and the complex conjugate, same angle or negative angle, and then you had the pole somewhere there on the same angle, but not on the unit circle, but close to the unit circle. And I think it's quite much closer than what I draw here. So now when you do the math, basically take these parameters back to the well, the zeros and poles to system coefficients B and A, and you quantize those to 8-bit precision, meaning, well, I'll show you what it actually means. So we are not doing it exactly 8-bit precision, but say close enough approximation to see the effect. But anyways, so you have a after that one you would have let's see, underscore B, let's mark them stars, okay, and you do then the analysis of the system. For example, what the zeros and poles would look like. These will change a little bit somehow. It's not guaranteed that even the 0 will stay at the unit circle. And then the pole will move somewhere. But this is quite common effect. The rounding effects actually will move this one to, well, either on the different direction on the angle, so they are not lined up anymore. So this pole does not anymore compensate the 0 totally on the amplitude response, but you will start getting a tilting of the gain. Okay. Another one, of course, from the same region, when you do the frequency response, the original would look like that, and for the same reasons, actually, this might look something like this. So you don't get the unity gain anymore, and you might actually even get the this notch angle to change a bit, and the attenuation is not necessarily anymore that infinite dB. Doesn't chip down to 0. What else I'm asking? Attenuation, bandpass change, bandpass ripple. Okay. So yes. So that kind of things will happen, and the passband ripple means basically how much you get variation on the passband. Okay. Then I have bandpass filter to match the following properties, and basically I think this is also a it might be also a part of the previous exercises, so it might be a free the point there, but anyways, the next one again, comparing direct form, or actually how many bits should be used if the system must implement a direct form filter. So here you have the design, the original design on the tree. Maybe I should take a couple of pictures and who put this there? One. Don't worry. Okay. All right, so how many bits? Meaning that first you will design a filter that fits the parameters what I'm telling you, okay? So a filter that fits those points. So you have the cutoff frequency 1, cutoff frequency 2, and then stop band start frequency 1 and stop band start frequency 2, and then you have some ripple here, okay, and the stop band attenuation. I think the both bands were at the same, but anyways, first you do the floating point design. You will get something like whatever you get. It will fit, whoops, it will fit your amplitude response picture. On floating point, it must do that. Okay, when you start reducing the calculation accuracy on direct form, you would quite soon get, say, a filter which does not quite fit there. So basically it goes, on that point it goes off your region of interest or your design region. Okay, and then you just basically add bits until it fits there again. That's how many bits you need. It could be say 7 bits or 13 bits or something like that. Don't worry, it doesn't need to be power of 2. For good obvious reasons. If you are doing actually a implementation on, for example, a FPGA, you can use odd number of bits for calculations quite easily. And another thing, if it's required to have only 13 bits accuracy and you are using 16 bits, it means that you don't need to worry about the overflow of the value if you are using second order systems. Okay, on second order you can always just do at least 3 additions before it overflows for the 13-bit accuracy on the 13 bits, signed 13 bits. Okay, good. But anyways, so that's the idea on the fourth and fifth exercise. So basically you get 2 points of answering these. So how many bits are needed in order to still meet the requirements? And the same question about when you do the second order sectioning for the filter you designed on part 3. How many bits are required? My guess is that you will get on the 45 exercise, you will get a higher number than in 67. Otherwise, you have done something wrong. Since second order section, as I already told you, it will give you better accuracy by itself. Okay, you don't need that many bits there. All right. Then 8th, since you have been already taking Chaos Modern Computer Architecture course, this is basically should be walking in a park. You just need to figure out how many Mac operations you would need in a bit system to do, let's see, the previous SOS. So basically the previous means that question 6 and 7, second order section. Yeah. Single time step on a fixed point platform. And then again, assume that the native word length is long enough for the required Mac operations. You no need to check if there's overflow or not. Of course, the overflow would cause some, or checking the overflow would cause some the extra overhead or extra bits you need. Okay, then have you been using Raspberry Pi 3 already? Everyone? At least, have you seen one? I can show you one if you don't want to. Okay. And then this is also performance calculations, how many channels Raspberry Pi 3 can theoretically manage running the previous filter. So, yeah. You can, you will earn some extra points if you can estimate also the overhead. Since this is a single core processor, basically, and or single cycle system, so basically it doesn't have much of parallelization, but then there's of course some overhead on breaking these systems into second order sections. Yes.
Are you mostly interested in the speed of the CPU by itself because it's 4-core system that has the neon instructions, so there are Mac instructions in the Raspberry Pi.
Excellent. 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 You just added some more work. Or I also give you some hints how to do it. I have done similar kind of tests in some processors, and you can actually make just a single simple loop shown in my first slide. Make a Mac loop and test it. Okay, where is it? Okay, make a Mac loop, multiply accumulate loop, long enough, and test the system performance. That's the easiest way of doing it. Just test it. Simple, short program, and run it with some timers and to check how long it actually takes. Performance meter. Oops. Okay. Yeah, Pi 3. It's 4-core. And now basically depending on the compiler, can it do the good usage of those 4 cores and max. The best way would be to run it actually a test code. A test code. All right, and hey, you all have some sort of laptop. You can actually do the estimation of how many channels your laptop could, in theory, or actually in practice, more or less in practice, to handle. I will show you a couple of tools for MATLAB. It's very simple to calculate or test the performance. Yes? The answer? The question? Yes? Oh, basically we have this same filter. And if you have multiple channel input and you want to actually do those more or less real time, basically you just run this one the same. No, not like that. So same system, but you need to process different input channels same time, simultaneously, more or less simultaneously. Of course, well, by default, I would say it's easy to handle just 4 on on this Raspberry Pi because it has 4 cores. But of course, you can handle much more, and you can actually use that. What was this performance scaling factor kind of thing? It has formula 1/1 minus 1 Amdahl's, yes. You can use the Amdahl's law if you want to do the performance calculations. And actually that would be the correct way. It's number of channels, and then there's the also you can then, if you know the overhead time, then you can get a quite good estimate for the for your system. But anyway, so number of channels, meaning there are different channels, different inputs requiring different outputs, and how many of these blocks you can handle.
That's, for example, how many videos you can
Yeah,
convert at a time.
yeah, or how many audio streams. How big audio mixer you can do on Raspberry Pi. All right. So we already know that you can handle about 3 100 megabits per second these internet lines or TCP/IP lines at the same time with the Raspberry Pi. Was it 3 or was it 2? It's one of the exercises actually. You should remember that. I do, and I haven't taken the course. but anyhow, so how many of those at the same time? Good. And next, let's go and take a look at the MATLAB and how to do some of that stuff there. Okay, good. All right, so this is actually exercise 6. IIR. Oh, not IIR. This embedded systems. So basically, this means the rounding errors. Etc. Okay, so let's start with some filter design, and I'm lazy. I'm using the FDA tool to do it. Or the tool. FDA tool, I meant. Yes, I did mean FDA tool. Just a moment. Also, okay, so that doesn't show up anything there. Close it. FDA tool, and I'll take low pass FIR equiripple. Let's see. Minimum order. Just for fun. Let's see how many orders do I get. Designing a filter. So it's 46th order. Oh, that will be actually showing up some rounding errors. And why it shows up me a lot of rounding errors is because of taking a look at the parameters. So this is the direct form coefficients here, where the biggest numbers are at the middle. So it's roughly 0.5. And the smallest one is actually on the edges, so this is 0.0014. So it's 2 decades smaller number there. So if you're thinking of a system which has only 8 bits presentation, that would have nothing there, since you have 7 bits plus sign. Or, well, precision, 8 bits precision means, well, plus 1 bit for the sign. All right, you can use the FDA tool to do the exercise, but basically you can, since some of you are using Octave, I'm actually taking this and take the coefficients to direct form. Only doesn't make any difference. What is the direct form one? For example, import the filter. What? No, sorry. Let's take it over. Ah, what happened? Something strange happened here. I'll start over. I'll start over. Oh, it was import from workspace, sorry. Export to workspace as coefficients, yes. Num. Well, I call them HH. Okay, that's how you actually get those coefficients to MATLAB workspace. Okay, which means that now I can play with them. So zeros and poles for those are right here. Okay, so these zeros are actually doing the low pass part, or the stop band, and these zeros are actually adjusting the gain to the more or less unity gain. Okay, and then frequency response. Frequency response of the filter, there we go. Okay, so it looks like that. It has a nice 80 dB the attenuation on stop band and about 1 dB ripple on the pass band. There. All right. Allow me to know it doesn't. Okay, and now next what we will do, I will quantize the these filter coefficients, and I'm checking from quant. Yeah, discrete value for multiples of quantity. Okay, that's how you quantize it. So for example here, quantize values of x within 0.1 accuracy. Now we have actually the sum of this filter, meaning the highest or absolute sum of this filter is actually the highest possible gain for this filter. Okay, I think it's 1. No, it's 1.98. Okay, so basically that defines the highest possible value if you're thinking the input ranging from -1 to 1. So basically the accuracy of the filter should be related to that value of the quantization level. So 8 bits from that one. Does it actually make any sense? Yes, it does. So in the worst case, you have a signal which is varying, so that you will have on the positive values of the FIR system, the positive values are actually ones, and every time when you have the negative value on impulse response, you have -1 input value. Then it would add you the worst case, the biggest value or gain what you can get out of this system. That's about 2. All right, so our quantization step size here for 8-bit system would be this one divided by 2 to the power of 8. Okay, and I'm kind of neglecting here the what is the sign bit actually doing. So I'm just taking 8-bit accuracy. 8-bit sign value has 7-bit accuracy. Right. This one is the first bit is for the sign. There are also unsigned filters, but nobody uses them. They're awkward to use. So that's the quantization step size for 8-bit clefs. Okay, and now you might be asking why I'm actually doing this. Is still in floating point. Yes, you can easily then basically move it to the fixed point. Just take the corresponding integer value, using that as a bit size. But for that then requires just some gain at the end of the filter, rescaling gain. Okay, but quantization step size. So now it is Q is quantized HHQ step. There, and let's compare these. So let me stem plot the HH just for fun. Where did it go? Figures. Yeah, okay. That's the original. And then let's see, I will somehow show also the quantized values. Hold on. And stem HHQ. It's red. Oops, not too red. And these are the quantized value. not much different, right? So some of them are actually exactly the same. Okay, but some of them are actually quite close to zero, where else where it actually should be non-zero. And the effect of this one, let's take another figure. Never do this one. I'll do it just for fun, since we have only zeros here. I'm actually plotting these new zero positions as poles. They are not poles. Oops. And then the oh, wow. Ah, okay. So basically, it's a, let's try it other way around, since I think this one became so unstable that it doesn't even calculate the yeah, some of the poles actually went off scale. But anyways, as you can see on the zero pole plot, all right, so all right, they are quite different. So pole location, not poles, but the zeros were actually moved. So original are those x's, and the quantized pole, the zero locations are those o's here. And we even have one O at the origin. Okay, that was the problem there. And then we have this. Okay, this looks a bit different, and which means that I would guess that the frequency response also looks quite different. Maybe I need to calculate it. Let's see. First, the HH 1024, and like that. Then I calculate maybe like that. That's the original. Then let me plot maybe it's already there. Well, we'll see what happens. Okay, good. Maybe we can just do it like this. Ah. Okay, original, and this is the quantized. Original 80 dB suppression on stop band, quantized 35. Otherwise it still looks, say, quite okay, except the stop band attenuation gone forever. So definitely, if you need that in this picture, it would mean that you would actually jump the stop and attenuation somewhere here. It doesn't fit into your design region anymore. Okay. Which means that if this was the system you were trying to implement, then basically you should do something about it now. And I claim that, okay, if you do it on second order sections, you would do much better. There are actually some functions to do it. Was it TF2? Okay, TF2 SOS. So transfer function to second order section forms. All right, so you can actually do a second order sectioning for this filter. So basically it gives you the second order section matrix like that, and basically it's still the same thing. So it does the magic for you. It's still the same system, but now on cascaded second order system. And actually you can use on the filter, you can use the second order system matrix as an input parameter there, I think. We'll see. So transferring. So HSQ, not HSQ, but H8. So we start from the original. So H8 SOS is same as transfer function to SOS of H8 and hello. Hi. 1. I think that's the way. All right, and basically we got this matrix. Let's take a quick look what it looks like. Yep. So it's still FIR. If you're taking a look at this help of the system, well, let's see. If you take a look at the help, so there's the each system has the parameters B and A in that order, and every one of these A parameters here is actually 0, except the first order. So this is cascaded FIR systems, and it's supposed to be good. All right, so now we can actually quantize these parameters. Quantize, let's see, each of these rows. Actually, we should do it separately since the first row has also the gain factor on it. And that's, I will do it on loop. For I equals to 1 to 26, good. And basically the rest of that, I will just take that each row 23, sorry, yes, of course. It doesn't allow me to break it in 23. Okay, 23 rows, and each vector should be quantized separately. And for the first part, we don't need to quantize the second part. It's already there. So basically, I can let me first separate each of these rows equals to HHSOS, all values of, let's see, first row, okay, II, and all values of that II row II, and then I'll just do HHQRR, or actually QSOS, ooh, equals, or HHSOS, Q is better. Okay, I quant of ith row and or values on that one will be quant size of RR. The step size now is basically absolute sum of RR 1 to 3, only those values, and well, let's see, divided by 2 to the power of 8. Yes, I think that's right. So I'm doing this still the same. So the worst case scenario of your filter is when you have the just opposite signs of the input, okay, and basically that gives you the quantization, the full range, and then divide that full range with 2 to the power of n bits. Okay, that's your quantization step size. Okay, hopefully it will work. And I had now this another one which has a little bit different numbers. Well, it seems that the 1 is not anymore 1, but well, things like this happen. I should have actually taken only the 3 first values to change. Yeah, I can. Yeah, yes. Yeah, column 4. Oops, what happens? Oops. Ah, not that one. Let's close that one. So I will just that was column 4 equals to 1. There we go. And basically, just for fun, make sure that 5 and 6 are actually still zeros. They're supposed to be 0, should be quantized to 0, but anyways, you never know. That was just, you know, some adjustment. Okay. So now I quantized SOS values. I can run it back to the direct form values or the transfer function values for the filter. I'm not sure if the SOS values are actually directly, you can use those directly on those systems, but well, back to direct, the transfer function. But this is just for the analysis. In reality, we would use these the values what are on this HHSOSQ. So HHQ2 is the SOSQ transfer function of HHSOSQ. Okay. Help on selection. Where is help on selection? There. We might actually also end up having some gain there, but well, I'm lazy. We can always, you know, do the gain afterwards. And now testing. So we had some figures here. So that was the quantized. This was original. This was the quantized. And let me add here the quantized, but implemented as second order section. Hopefully this will be better. Oh wow. Okay. So we are actually back to almost the original design. So we have the 80 dB attenuation on stop band, and we are using 8-bit precision on the calculations. So basically this is the direct form calculations, meaning the long convolutions, one single system doing a long convolution compared to a system which is breaking down in second order sections and doing these short convolutions, but plenty of them. So cascaded system, much better performance. Or actually this is almost, well, it's not the same, but well, it's hard to tell. I think we are just missing 1 0 here, and more or less it's about the same system. Okay, how about zeros and poles? So this is how much the zeros and poles differed from the on the original and the direct form implementation. And this is how close they are on this new design. Okay, well that's the way it's supposed to be. So they are almost the same. Oops, not that one. Oh, wait a second. Oh, 7. Oh yeah, okay. 2 and 7. Oops, 2. Which one was there? 3 and 7. Okay. So that's how close you get with the second order systems, and then this is how far it was for direct form. Okay, so that's how the quantization error actually makes a big difference. We could have actually tested how close we are getting. Okay. Interesting. Okay. For example, on the let's continue on this one, since it seems that with the 8-bit precision we are still quite okay with the calculations. Now we could easily go down with the bits and try how far you can go on the second order system implementers, how many bits you actually need. Okay. So let's take the HHSOS. Oops, that was the for loop. Do I want to do the for loop again? Well, maybe. For example, let's make it 6 bits. Six bits. We are getting a little bit off on the on pass band. We are still quite okay with the stop band. 6 bits. It's not much. 6-bit accuracy is not much, but still we are having at least some sort of filter. It's, you know, it's still something that you can work with. Okay. But I would guess that 7 bits would be maybe a little bit closer to the yeah, 7 bits. We are still on the design region, no problem. So that's how you test the how many bits you need in order to still produce the same filter. Okay, on IIR system, pay attention actually this one. So the multiplications, accumulations, where they are done, if they are done separately or not. Think of the second order system that basically you have the forward section and the feedback section separately. So basically you need to quantize quantize the forward section, which is the first three parameters on this one, and then the quantize differently with the that feedback section. Okay. With similar manner though. All right. So let's take a quick look at these. That's what 6, 7. Okay, and then just minor thing about the. Well, let's take a look at FDA tool. Now you know the heavy part. I will show you the. Easier way of doing it. Well, it's not necessarily easy, since it's easier to make also mistakes on this system. So for example, I will start with the maybe IIR maximally flat 8th order. Well, that's just fine, any system. Okay, so that kind of system, actually you can in here turn on the quantization. Okay, double precision is what we are doing. It's 40 bits, and this is single precision would be, it's still fairly accurate. It's, you know, but then you can also do the fixed point width. Okay. Okay, gimme. Okay, with the word length, and here we actually have the word length of the system. So we can try, for example, 8 bits. Oh no, that's not right. Okay, but anyways, this is 16-bit best fraction, or well, okay, here 8 bits. There we go, and it's still okay because we have a second order section division here. I think we can change it to, oh, sorry, not from here. From here, we can convert this structure to, for example, direct order. It always gives me the. Okay. For good reason, it doesn't have anything else to offer than second order system divisions here. Okay. It doesn't make much difference then. But you on the previous version, it also had the direct form. You could actually compare it. Not anymore. Okay, it was so much better. Everything was so much better earlier. Not. Okay, but anyways, some of these designs you can basically do with the FDA tool. And why I'm showing this one actually is that when you have a filter design done in FDA tool, you can do although also the phase responses and then the phase delays, impulse responses, step response, zero pole. Okay, let's say fixed point. All right, and coefficients as second order system coefficients. And you can actually take all of this to, let me see if I'm okay, that one was okay. You can actually take this one into your system design. There you have a C header file having fixed point 8-bit numbers for each of those the filter SOS sections. So you just need to implement the SOS subroutine in your embedded system, and you can take the filter coefficients from FDA tool directly. And they come as, you know, this is integer values now. All right. It's a little bit too easy, I know. What? For example, on your, you're using some, was it NXP processor you're using on Chaos course? So if you want to, yeah, LPC stick some. If you want to try a digital filter there, you can design the filter coefficients on this. Oh, you just shook your head. Hey, that sounds like your personal the eighth exercise. Okay, but so yeah, that's it, I think, for today. Except, okay, good. That's so performance. They're actually functions. Tick and tock. Oops, not TICC, tick. Tick and tock. This one. MATLAB function tick actually starts a stopwatch time to measure performance, and tock reads it. So basically, you can do all sorts of things like performance estimations. For example, now I have filter coefficients. I could do some filtering, or actually, let me just do a tick and tock on the frequency response. Oh, that's a frequency response. How long it actually takes to calculate 1024 points of this system frequency response. Okay, it took about 6.6 milliseconds. Next time it's faster. Third time even faster. Why? Well, this is not just a command line interpreter. It remembers something. So basically, after a few times, the MATLAB has optimized the performance of this operation. So if you're doing performance measurements with tick and tock on MATLAB, you need to actually take into account that there's always some overhead of calling a new function or new line of interpreter. So if you do it multiple times, the actual system, the MATLAB actually is learning what you tried the last time, and it has some of the functions already on the memory. So basically, it's this dynamically linked executables that are on computer memory. Okay, and if you get those from disk, as I was calling it the first time, it started looking on those on the everywhere, you know it. Every place on the computer, and the last place would be hard disk. So whenever you take a command that hasn't been used for a while, it's on hard disk. Fundamentally, it's on hard disk, cached there. Okay, so it takes a longer time, of course. But then you run it a few times, now it's on the local cache, and finally it's about 0.7 milliseconds anymore. So running a few times the tick and talk will give you some performance numbers. And now you could actually try, for example, the 10th exercise is how long it takes for the MATLAB to do the same filter, or how many channels you can do. You basically make a data set of some number of samples, and for example 1 second long data for your filter, and see how fast it goes. So that's then just divide 1 over that value will give you how many channels you could in principle handle with that filter on MATLAB. Okay, that's all for today. So good luck.